Hi, this is John Whitaker, and this is our 6th video lecture for the probability class, the graduate level class. And hello Wayne, hello Travis. Today we want to look at two particular discrete random variables and know some characteristics about them. And so the first one is called a Poisson random variable. Here's its definition. So a Poisson random variable is a random variable x that is a discrete random variable and it is defined by its PMF, and whose PMF is f of x equal to e to the minus lambda, lambda to the x, all over x factorial, where x is allowed to be 0, 1, 2, 3, forever, and lambda is some fixed number greater than 0. So to be Poisson, your PMF, your discrete random variable, your PMF looks like this for some fixed positive lambda. Well, the first thing I'm going to look at is for that PMF, we want to show that if we were to sum it up over all x values, output values, big X, that's from 0 to infinity, well, then we get 1. To do that, let me remind you of Taylor's theorem. So, at least abbreviation of it. What it says, if you remember, is if there's a power series representation for f of x, a function, then what it looks like n running from 0 to infinity of the nth derivative of f evaluated at some number a times x minus a raised n all over n factorial. In particular, the Taylor series expansion, and when you let a be 0 for e to the x with a equals 0, it's called the Maclaurin series. What it's equal to, it can be shown that that's equal to the sum as n runs from 0 to infinity of x to the n over n factorial. So that's its representation. And thus, if we look at the sum as x runs from 0 to infinity of f of x, the PMF for a Poisson random variable, then that's equal to the sum as x runs from 0 to infinity of, let's see what this was, it was e to the minus lambda, lambda to the x all over x factorial, which is equal to the sum as x runs from 0 to infinity. Well, I can take out the e to the minus lambda, and I will take that out. And then I have lambda to the x over x factorial. If you compare this sum and what's behind it to what's written here, you have something raised to the index, something raised to the index. Okay? All over the index factorial, and the index running from 0 to infinity. It's the exact same thing. And so the e to the minus lambda, I'm going to write that down. But this sum is going to be e to the, what was the variable that was right here, that's e to the lambda. And so when you have e to the minus lambda times e to the lambda, that just gives you 1. And so we notice that as we expect, or as should be, the sum of the PMF over all x values is equal to 1. Next thing I want to look at is what the expected value of Poisson random variable is. So it's a fact if x is a Poisson random variable, and I'm going to say with, in parentheses, a parameter. So what distinguishes Poisson random variables among themselves, what distinguishes them, is the value of lambda, with parameter lambda. Then, the expected value of x is also equal to lambda. Let's prove this fact. So we let x be Poisson with parameter lambda. Then the expected value of x is equal to the sum over all x values, x runs from 0 to infinity, of x times e to the minus lambda, lambda to the x all over x factorial. That's the EMF. Well, the one thing I noticed is when x equals to 0, the first term of the sum is 0, so that doesn't contribute anything. So I might as well run it from 1 to infinity. So that's what I'm doing. So that's equal to the sum as x runs from 1 to infinity of x e to the minus lambda, lambda to the x over x factorial. And so one thing I noticed is this x, along with all the factors in x factorial, which has an x, there's an x here at the top and x in the bottom, we can cancel. This is sum as x runs from 1 to infinity of e to the minus lambda, lambda to the x over x minus 1 factorial. Now let's pull out an e to the minus lambda and a lambda. So when we do this, we're left with the sum as x runs from 1 to infinity. I can pull those out because they're constants with respect to x. I'd have lambda to the x minus 1 over x minus 1 factorial. Now, let us make a change in index here. Let's let y equal to x minus 1. So this is equal to e to the minus lambda, lambda times lambda. Here this will be the sum. Now y runs from 1 less than what x ran. So y would go from 0 to infinity. This will be lambda, and wherever we're seeing x minus 1, we put y over y factorial. Well, by Taylor's theorem, we know what that is. So this is e to the minus lambda. It would be times lambda, and here's e to the lambda, and that's just lambda. So that concludes the proof that the expected value of Poisson random variable is lambda. Next, we're going to look at the variance. So it's a fact. If x is a Poisson random variable, with parameter lambda, then the variance of x is also equal to lambda. So the expected value and the variance are the same here. They're both lambda for some random variable. And let's see if we can prove that fact. We let x be a some random variable with parameter lambda then the variance of x by formula is the expected value, x squared, minus the expected value of x to b squared. We've already got the expected value of x as lambda. Well, we don't have the expected value of the quantity x squared, so let's work on that. So let's note that the expected value of x squared, well, our definition of the expected value of a function of the random variable x, it's the sum, the discrete random variable, over all output values, so x runs from 0 to infinity, of g of x, which here is x squared, and then times f of x, the PMF, which is e to the minus lambda, lambda to the x, all over x factorial. Like we saw before, when x is 0, the first term in this series is 0, so no use writing that. So we'll say this sum as x runs from 1 to infinity of x squared e to the minus lambda, lambda to the x, all over x factorial. And again, we can cancel out one of those x's, so this is equal to the sum as x runs from 1 to infinity of x e to the minus lambda, lambda to the x, over x minus 1 factorial. Now, what I'm going to do is I'm going to pull out a lambda. So that's lambda times the sum as x runs from 1 to infinity of x times e to the minus lambda, lambda to the x minus 1, all over, my sum should be a little bigger, all over x minus 1 factorial. This and this index passed, that's a good thing. We're going to let y, again, let's change variable here, equal to x minus 1. So we get the sum, well, it's got a lambda out front, so it's lambda times the sum as y runs from 0 to infinity. Well, here's x, so instead of x, what I'm going to write down is y plus 1, e to the minus lambda, lambda to the y, all over y factorial. That's lambda times, this is the sum as y runs from 0 to infinity of y, e to the minus lambda, lambda to the y over y factorial. And then plus, so I'm distributing the e to the minus lambda, lambda to the y over y factorial into this y plus 1. So plus, and then splitting it up into two summations. Y equals 0 to infinity, it would just be e to the minus lambda, lambda to the y over y factorial. I think I got room to put it here. This is equal to lambda. Now, what this is nothing more than a Poisson random variable with parameter lambda. And so we found, it's, this is the PMF of it, times y, and you sum it all up, that's the expected value of y. So it's expected value. Well, that's just lambda. The expected value of this is lambda. That's a lambda. Okay. And then plus, here is the sum of the PMF of a Poisson random variable, okay, with parameter lambda. It's a y here. And so what we get here is 1. So we end up getting lambda squared plus lambda is what the expected value of x squared is for Poisson. Okay, so the variance of x, and this Poisson variable, is equal to expected value of x squared minus the expected value of x, and that's equal to, here, this was lambda squared minus lambda, it's plus lambda, minus, this is the expected value of x to be squared. Well, the expected value of x we found to be lambda earlier in this lecture. So this is minus lambda squared, and indeed that's lambda. That is that. Let us now look at an example. Let's say, suppose the number of typos on a page of a book is a Poisson random variable with lambda equal to 1. And let's ask this question. Let's find the probability that there is at least one typo on that page. Okay, so to symbolize the question, what we're being asked is what's the probability that x is greater than or equal to 1? Where x is Poisson with lambda equal to 1. So that means that we have at least one typo. Well, this is 1 minus the probability that x is equal to 0. Property of probability. Well, I know what this is. This is equal to 1 minus, and the probability that x equals 0 is f of 0, which is 1 minus e to the minus 1, but 1, lambda raised to the 0, all over 0 factorial. You might remember that we had the convention that 0 factorial is 1, so this is the same thing as 1 minus e to the minus 1. And I think if you use your calculator, you'll find that that's approximately equal to 0.63. All right, kind of a fact and comment. I was listening to comment. It says, a Poisson random variable can be used to approximate a binomial random variable when n is big and p is small. Okay? Remember, n is the number of trials for a binomial random variable, and p is the chance of success. Well, let me give the idea, sketch a proof of why this is true. So this is the sketch of proof of this comment. And so here's what it is. Note, if x is binomial, then the PMF, f of x, is equal to n choose x, p to the x, 1 minus p to the n minus x. And here again, x runs from 1 to all the way to n. Well, let's look at this. This is f of x to be rewritten as n factorial over n minus x factorial x factorial, p to the x, 1 minus p to the n minus x. Let us rewrite this fraction here, which I'll rewrite as the n factorial over n minus x factorial. I'll write that down as n times n minus 1 times n minus 2 times, all the way down to times, it's n plus 1 minus x. And that's still all over x factorial. And here I have p to the x and 1 minus p to the n minus x. Okay, we're going to make the following substitution. We're going to let lambda be equal to n times p and, or thus, p is equal to lambda over n. So here's what I can write for f of x. It's equal to n times n minus 1 times n minus 2, all the way down to n plus 1 minus x and then I'm going to write down x factorial as what's there. There's p to the x, but I'm going to write that lambda to the n raised to x, and then 1 minus p. Well, there's 1 minus lambda over n raised to n minus x. I'm going to rewrite this. This is equal to n minus 1 times n minus 2 all the way down to, let's write this as n minus and it would be x minus 1 over, instead of the x factorial, we'll leave that x factorial at another part of the fraction. But here we got lambda to the x, and then there's an n to the x. I'm going to write down n to the x over here to get this part together. And then here I'm going to put the x factorial. Here I'm going to rewrite this as 1 minus lambda over n raised to the n, and as a fraction put 1 minus lambda over n raised to the x. As we rewrite this as 1 minus lambda to the n raised to the n times 1 minus lambda over n raised to the minus x, and pull the minus x part to the bottom and make positive x. And then we'll look at each part of these. Okay? All right, now, first thing we're going to do is note that the limit as n goes to infinity, so this is something you can check out, of n times n minus 1 times n minus 2, all the way down to n minus the quantity x minus 1, all over n raised to the x. Now, as n goes to infinity, this goes to 1. So what happens is that, look, in the top you have exactly x number of terms, and they're over n times itself x number of times. And it turns out as n gets really big, x being fixed, that the fractions really stay close to 1. Okay? N gets really big, and so that multiplication stays close to 1. That can be shown. So as I move on, as n gets really big, this part is like 1. I'll write that down. So when n is big, this n times n minus 1, n minus 2, all the way down to the multiplication of n minus x minus 1, all over n to the x, is approximately one. Okay. Then also want to note another part of the way that we wrote the p about this 1 minus, the limit is n goes to infinity, of 1 minus lambda over n, okay, raised to the n. This is equal to e to the minus lambda. So again, so when n is large, 1 minus lambda over n raised to the n is approximately e to the minus lambda. Now, let's look at another aspect in that PML. Note that 1 minus lambda over n raised to the x is really the same thing as 1 minus lambda, 1 minus, well, lambda over n was represented by p over x. And what we said was, if we're looking at when p is really small. So here, when p is really small, 1 minus that, that's going to be approximately 1 raised to the x. And that's just equal to 1 because of that, when p is really small. So, so when n is big and p is small, the PMF of a binomial random variable x f of x equaling to, it was n times n minus 1, n minus 2, all the way down to n minus x minus 1 over n to the x lambda, I think it was lambda to the x over x factorial, and then we had 1 minus lambda to the n over n, 1 minus lambda over n to the x. That is approximately, this part we said was 1. Here, this is lambda to the x over x factorial. You leave that alone. This part was like e to the minus lambda, and this part was 1, which equals to the PMF of a Poisson random variable. So that's the sketch of the comment I made. Sketch of the proof of the comment I made. Well, that's all I want to say about a Poisson random variable. Okay. Next thing I want to do is talk about the second random variable that I want to today, and that's the geometric random variable. So here's the definition for a geometric random variable. It says, suppose a Bernoulli experiment is performed independent time until the first success occurs where the probability of success on each trial equals to little t. We're going to let x count the number of times the experiment was performed. Until the first success occurs. Then x is called the geometric random variable. So that's the definition of a geometric random variable. Sometimes it's similar to a binomial random variable, but it's different. See, a binomial random variable, we have a fixed number of times that we do the experiment. We just count the number of successes. Here, for geometric, we only want one success, and we just count the number of times the experiment had to be done to get that first success. And so, as a fact, if x is a geometric random variable, then the PMF is f of x. Let's think about this. So you're going to be getting failure, 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 and then you get a success. So how many failures did you have? Well, x is the number of times that you want to do the experiment to get the first success. So the failures, there were x minus 1 of them, and the chance of a failure is 1 minus p. And the last guy has to be a success, and the chance of that is p. So they're independent, so that's why you have this multiplication. Okay? Where, well, x could be 1, because you could have got a success the first time you did it. 2, 3, correct? Okay. Now, why is the geometric random variable named so? And that's because if you sum up, as x runs from 1 to infinity, of p times 1 minus p raised to x minus 1, what you'll notice is that you can factor out a p because it doesn't depend on x, it's constant. Sum as x runs from 1 to infinity of 1 minus p raised to x minus 1. And with p being a positive number, same between 0 and 1, let p be a positive number, then here this becomes a fixed number raised to the index, and that is a geometric series. And that will sum, converge, I should say, to a specific number. It is the first term in the series, and here when x is 1, we get 1, over 1 minus the quantity being raised to the power, so that's 1 minus p. Okay, right here I have room, I think. This is p times 1 over, well, 1 minus 1 is 1 minus the quantity 1 minus p. It's just p at the bottom. So p times 1 over p, that's just 1. And so the sum of the PMF for a geometric random variable over all the x space it can take is 1. That's what we expect it to be. And the reasoning has to do with the use of a geometric series. That's why I've got the name it does have. Well, I want to look at the expected value and the variance for a geometric random variable. Okay, so as a fact, if x is a geometric random variable, and sometimes we say with parameter p, then the expected value of x is it's 1 over p. Expected value of x is 1 over p. We won't prove this fact. We'll do this symbolically. Okay. So we're going to let x be a geometric random variable. Then, the expected value of x, well, it's going to be the sum over the x value, well, that's 1 to infinity. Here's going to be x times the PMF, which is p times 1 minus p to the x minus 1. So definitely I can take out a p here, and I will. So this is equal to p times the sum as x runs from 1 to infinity of x times 1 minus p to the x minus 1. Now, what we're going to do is we're going to consider this 1 minus p as a variable, even though p is fixed here. And we're going to rename it as q. So that we can symbolically get in a situation where we can figure out what this sum is. Okay, so what we have here is we're going to let 1 minus p be symbolized by q. So the expected value of x is p times the sum as x runs from 1 to infinity of x times q to the x minus 1. Think of q as a variable. And this quantity looks like the derivative of q to the x. Bring down the x, something raised to 1 less power, the variable raised to 1 less power. And so we'll say, hey, that's really equal to p times the sum as x runs from 1 to infinity of the derivative with respect to q of q to the x minus 1. Now, we can pull this limit outside the sum, and I'm not saying why, but we can. That's p times the derivative with respect to q of the sum, as x runs from 1 to infinity, of q to the x minus 1. Now, here the q again is some number between 0 and 1. This becomes like a geometric, or is a geometric series. So we have p times the derivative with respect to q of the quantity. What does this sum add up to? What it adds up to is the first term, which is 1, over 1 minus q. All right. So what is this going to be? I have made a mistake. Let me look here for a second. Yes. So really this notation should be 0. 0. And here it's q raised to the x. Gosh. And this is raised to the x. That's what this is. So that's the way that we think of this derivative. So with that being written, here I think this is 1. Sorry. So, right. But here this is the same thing when you pull out the derivative. You get from x running from 0 to infinity. It's the same thing as that. Okay. We check that out. Make sure that's accurate. Okay. And now here's where we are, except I miswrote what this summation is. The first term in the summation is, here it's 1. It's not really changed to 0. It changed to 1. No, I'm going to need to check that out. So here, I'm saying this is q over 1 minus q. All right, I need to check out from this step to that step. I'm sorry, but I'll verify that for you next time. And that's equal to, so I want to take the derivative of this with respect to q. So I'm going to use the quotient rule. So I'm going to write down 1 minus q, the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is minus 1, all over 1 minus q to b squared. That's equal to p, and let's see, this is going to be 1 minus 2q all over, and the bottom becomes 1 minus 1, so what is q? So q is 1 minus p to b squared. So this is 1 minus 2 times 1 minus p all over 1 minus, there's p here. 1 minus 1 is nothing. Minus a p, at least, and that's p, b squared. So this is equal to, this is p squared. So the p's cancel out, leaving a p in the bottom. And here I have this is 1 minus 2 plus 2p. Not right. Oh, I made a big mistake. I'm sorry. I'm not paying enough attention. Okay. So there's the p. Let's back up. There's the p. Here's 1 minus q. Here's a plus q. That's just 1 over 1 minus p, all that p squared. Gosh. And that's just p. That's just p times 1 over p squared, and that just ends up giving 1 over p. There's a little bit of a problem here, so I won't take my time. I'm sorry. This lecture's going to run over a little bit. So, look, if I take the derivative with respect to q, I'll bring down the x, it's q to the x minus 1, x runs from 1 to infinity. This is exactly the same. Okay? Now, if we pull out this derivative, okay, that's all we're doing. Let's check this out. So here, the first sum, so what is this sum here? Forget the p for a second. This is the sum, well, it's written right here. The sum is x goes, as x goes from 1 to infinity of x times cube x. Let's look at this. So what do I want to look at? I'm sorry, I didn't look at this detail as well as I should have. So here, if we look at the derivative with respect to q, the sum as x runs from 1 to infinity of cube x. So this would be the derivative with respect to q of q plus q squared plus q to the third plus forever. And that will be equal to 1 plus 2q plus 3q squared plus 4q to the third, and so on. And that, I claim, is the sum x runs from 1 to infinity of x times q raised to the x minus 1. It sure is. And so that's how we get the exact same thing. That's what we have on the side. Check it out. When x is 1, we have 1 times q to the 0, which is 1. When x is 2, we got 2 times q to the first. When x is 3, we got 3 times q to 1 less power. And that is exactly this sum right here. They're exactly the same, so that's why these things are the same. Anyway, that concludes the proof. We have it. Let me hear on this small portion of the board. Write down the next factor we're interested in. That is if x is a geometric random variable with parameter p, then the variance of x I believe that's equal to 1 minus p over the quantity p squared. That's what we're going to show. So we'll do this proof. It's a little bit more involved than the previous proof. I'll be a little bit more careful, I hope. And then we'll do an example and call it quits. Okay, so here's the proof. We're going to let x be a geometric random variable with parameter p. Then the variance of x, which equals to the expected value of x squared minus the expected value of x to b squared. Note, we already have the expected value of x, it's 1 over p. But the expected value of x squared we don't have. This is equal to, it's a sum, as x runs from 1 to infinity, of x squared times p times 1 minus p raised to the x minus 1. So that's what we have. What we're going to do is write down this x in an innovative way. So this is equal to sum as x runs from 1 to infinity. We'll rewrite it as the quantity x minus 1 plus 1 to b squared. P times 1 minus p to x minus 1. So let us square this out. So this is the sum as x runs from 1 to infinity of x minus 1 to b squared plus 2 times x minus 1 plus 1, all that times p times 1 minus p to the x minus 1. Okay, let's break that up into 3 sums. That's the sum as x runs from 1 to infinity. The first one is x minus 1 squared times p times 1 minus p to the x minus 1 plus the next sum is x runs from 1 to infinity of 2x times p times 1 minus p to the x minus 1. It's x minus 1 here. And then finally, we have the sum, which is x runs from 1 to infinity of p times 1 minus p to the x minus 1. We've shown this is equal to 1. forgive me, this is the same thing as the first sum. Plus the second sum. Two times x minus 1 p times 1 minus p. Again, you know, that's to the x minus 1 is right up here at the top. And then plus 1, and that's what that is. Now what we're going to do is we're going to let, change the variable here, we're going to let y equal to x minus 1 in our sums. And so here we end up getting the sum as y runs from 0 to infinity of y squared p times 1 minus p raised to the y plus, here it would be the sum as y runs from 0 to infinity of 2 times y times p times 1 minus p to the y. And then here we have plus 1. One thing to notice as I turn the camera, when y is equal to 0 in those last two sums, the first term in each of those two sums, in that last line, would just be 0, the first term. So might as well start from when y is equal to 1. That's what I'm going to do. That's the sum as y runs from 1 to infinity of y squared p times 1 minus p to the y plus the sum as y runs from 0 to infinity of 2y, well, that should be 1, 2y times p times 1 minus p raised to the y, and then plus 1. And I'm going to say that's equal to, if I pull out 1 minus p, I've got the sum as y runs from 1 to infinity, y squared times p times 1 minus p, but I pulled out one of them, so it's the y minus 1. And what we're doing is that looks a lot like our original problem. Plus the sum, oh, let's pull out something. How about 2 times 1 minus p? Sum as y runs from 1 to infinity of y times p times 1 minus p to the y minus 1, and then plus 1 hanging around here. And so what we get, remember what we were trying to calculate? Well, let me write this so the symbols match up. Let's let y equal to x, just to change a variable to make the symbols match up, because that's what I'm looking to do. So this is equal to 1 minus p. This is the sum as x runs from 1 to infinity of x squared p times 1 minus p to the x minus 1 plus 2 times 1 minus p times the sum as x runs from 1 to infinity of x times p times 1 minus p to the x minus 1 plus 1. And so remember what this was equal to. That's the expected value of x squared. That's what we're working with. Is equal to. This is 1 minus p. And as I was saying, this is nothing more than the expected value of x squared. Plus, this is plus 2 times 1 minus p. And what this is the expected value of x, which we know, and then plus 1. So we're trying to solve for the expected value of x squared. So if I pull the expected value of x squared terms together, what we have is, what we get is 1 minus p times the expected value of x squared, that's what we get. I'll pull that term to the left hand side, equals to 2 times 1 minus p, and then it said the expected value of x, but I know that's 1 over p, and then plus 1. So this is p here, so this says the expected value of x squared is equal to, I divide everything by p, so here it would be 2 minus 2p, that's what that top is, over p squared plus 1 over p, or p over p squared. And that's equal to 2 minus p over p squared. So I get the expected value of x squared. So the variance of x is equal to expected value of x squared, which we just found, minus the expected value of x to b squared by our fact. And that's equal to 2 minus p over p squared minus 1 over p squared, 1 over p to b squared, so 1 over p squared. So we end up getting 1 minus p over p squared, and that's what we said. So that's the proof of that fact. Okay, I'm going to do an example, and then we'll call it quits. So last, this example, a card is selected from a standard deck and its suit is noted. Then the card is returned to the deck and the deck is reshuffled. This is done over and over until the first part is selected. Let x count the number of cards that were selected. That's the number of times this process was done. Okay, what can we say? Well, then x is going to be a geometric random variable with p equals 1/4. The p amount is alpha of x equaling 1/4 times 3/4 the x minus 1, where x is equal to 1, 2, 3, forever. Expected value of x, that's 1 over p, which equals 1 over 1/4, which equals 4. Yeah, on average, it'll take us 4 times to get the first part. And 3, the variance of x, that's 1 minus p over p squared. That's equal to 3/4 divided by 1/4 the b squared. That ends up being 3/4 times 16 for 12. Okay. So with that little kind of hesitancy and the proof about the expected value of a geometric random variable, other than that, everything looked good here in this lecture. We'll call it quits there, and we did fix that proof, so we'll find everything. So it's okay. All right. Thank you very much for your time.